You know, I always notice, I've been watching the newscasts on the channels, and they never go on camera with the talking head, the anchor, looking down. They always look up. So it's too late, but I'm going to start doing that probably, so that I can make immediate eye contact and establish the rapport immediately. I would remind you that, as we discussed right before, because I forgot when it was, we're having the final examination 10:30 this Friday, and it will be here in class. And the material in the examination itself will be cumulative. It will cover everything from the beginning of the course to the end of the course, with a touch more emphasis on material which we've had from the last test. You can be assured that you'll see some of the material since the last test on the examination. As before, the exam is closed book, closed notes. You're allowed 3 sheets of paper on which you can write anything that you would so desire, and you can have that accessible to you during the examination. The final examination will be much like the first 2 midterms in the sense it'll be problems and working problems. I'm going to have special office hours on Thursday starting at 10:30 in the morning, which is the time this class usually meets, until about 1 o'clock. So if you have any final questions, that's a pun kind of, isn't it? If you have any final questions, come in and talk to me there. Okay? Any questions on the final examination? Good. This was asked before. I do have last year's final, which I'll have posted. I'll have Hongbo posted. I meant to do it, but it slipped my mind, and I will do that. Okay. Any other questions? Okay, hearing none, we'll go ahead and conclude with some of the things in the lecture. Then, time permitting, we'll address any questions that you have concerning the course from the floor. We were talking last time about filtering wide-sense stationary random processes. And what we decided was something pretty interesting, and it was this, that if we had an input, x of t, going into a system, I always forget my pointer because my finger doesn't look good. Uh-oh. There's a good pointer. That if we have an input going into an output through a linear time invariant system, linear time invariant system is a system which can be characterized by an impulse response or by a frequency response, which is the Fourier transform of the impulse response, also the step response. How do you get the impulse response from the step response? Differentiate. That's right. Very good. Okay, and there's 2 things that we decided. Number 1 is that the input, well, here's the assumptions. The input is wide-sense stationary with a mean of m and an autocorrelation of r. Equivalently, the input has a power spectral density equal to the Fourier transform of the autocorrelation, which is equal to big S sub x. So we run this wide-sense stationary stochastic process through the linear time invariant system and generate an output of y of t. If the input is wide-sense stationary, so is the output. And also, we can determine the parameters of the autocorrelation and the mean of the output, the wide-sense stationary parameters, by knowing the parameters of the input and the impulse response of the system. And the relationship are given by the following equations. The expected value of the output is equal to the expected value of the input times the transfer function at the origin. This is a result that we showed last time. And then, interestingly, we like to relate the second-order statistics, the autocorrelation, through in the spectral domain because it's a much simpler equation. It says that the output power spectral density is equal to the input power spectral density times the magnitude squared of the frequency response of the system to which the input is being fed. So this is the relationship that we have for tracing a wide-sense stationary stochastic process through a linear time invariant system. Okay. Now, we went through a derivation of this. I do have a little footnote here that there is another derivation of this on page 415 of your text, if you'd like to take a look at a little more protracted derivation of this same equation. But it's fundamental for linear time invariant systems. We have a similar sort of case for discrete time systems where we have a linear time invariant system, except now things are in discrete time, an input x and output of y. We have the same relationship. The power spectral density relationship is exactly the same, and the mean relationship is exactly the same. So therefore, these are very valuable equations. They're applicable everywhere, including continuous and discrete time. If we have an input, which is zero mean white noise, then we know that the output always has an expected value of 0. If you put in something with a mean of 0, you get output. You get out something with a mean of 0. So the expected value of y of t is equal to 0. And the power spectral density is equal to n0 over 2. Since the power spectral density of the white noise is uniform, it's equal to a constant, the term for the power spectral density of the input is simply n0 over 2, and we're left with this equation. So this is a way you can sculpt, if you would like, any autocorrelation that you would like. You would obtain a impulse response, the magnitude squared of which was the power spectral density of the noise you wanted. And you could use network synthesis tools, be it in the discrete or the continuous time system, to evaluate such a linear time invariant system, and then you know that the output has a zero mean and an autocorrelation given by your impulse response. So therefore this is a good method of synthesis. See, I have 418 referenced in the book. I don't want to go there now. I will go to low pass, high pass, and band pass filters. It does turn out, of course, that if you have a high pass, band pass, and low pass filters, that these filters usually have a frequency response that is binary. By that I mean, for example, for a band pass filter, you might have a frequency response which is equal to this with a height equal to 1. Well, the interesting things about these sort of filters is that h is equal to h squared is equal to the magnitude of h squared if we talk about ideal filters. The reason being is that the filters only take on values of 0 and 1. And if you square 0, you get 0. You square 1, you get 1. So therefore, because of that, before we had this expression, it should be sy. And so now for filters, that's the same thing as h times s sub x. So this is true for any time that we're actually running through a linear time invariant system, which is a filter. This, of course, allows us to do filtering operations in the conventional sense. Suppose, for example, we had an additive signal, say a z of t, equal to an x plus y. And suppose that the x and y were statistically independent. If they are independent of each other, it's easy to show that the power spectral density of z is equal to the power spectral density of x plus the power spectral density of y, if they are independent and zero mean. In that case, we could actually perform filtering operations as is shown on page 418 of your text. Let's take a look at that. Can we zoom in on this, please? Thank you. Thank you. So here we have a power spectral density, and we have two components of the power spectral density. And this could be, for example, a signal-to-noise ratio. Again, page 418. So we have one component, which is a low-pass version, and the other one, which is a high-pass version. And these are power spectral densities of the underlying stochastic process. We can take this stochastic process and run it through a low-pass filter, and just as we would expect with deterministic signals, if we ran it through a low-pass filter, we would get out only the middle part, so we would get out the signal. Conversely, we could run it through a high-pass filter, shown at the bottom here, I'm sorry, that's not a high-pass filter, it's a band-pass filter. We could run it through a band-pass filter and only let out the high-frequency components. So we can filter the power spectral densities in much the same flavor as we filter deterministic signals. So the power spectral density, at least for the wide-sense stationary stochastic process, is a good way to think about stochastic processes in terms of their frequency components. We had one example when we listed all of the properties of the power spectral density that we didn't prove. We did prove the power spectral density function was even. We proved that it was real. What else did we prove? Oh, we proved that its area was equal to 1. No, we didn't. That's another density. What density is that? It's probability density. What's the area of the power spectral density? It's equal to the power which is delivered by the process, right? That's the area under the power spectral density. One of the things that we chose, however, to state without proof was the following property, that the power spectral density is non-negative. That is, in no place does it dip below 0. We now have the tools to indeed show that the power spectral density at no place dips below 0. We can do that by taking the result of the linear time invariant filter. Suppose that we had a filter that was a band pass filter, and it was from F0 to F0 plus DF, where DF was a very, very small increment. So this is our band pass filter. In essence, what we're doing is we're letting through a single frequency, right, of the stochastic process. We let through this single frequency of the stochastic process. We know that the output of this filter, if we, X is the input of the filter, this is the output of the filter, right? And the output of the filter is equal to the input of the filter in terms of the power spectral density times this h of f, which we have up here. So if we put the input through this, we simply multiply this by the power spectral density of the input to get the result. And here is the proof. The average power that we get out must be positive, right? Or maybe 0. But in general, it's going to be positive. No matter what stochastic process you have, the average power delivered is always positive or non-negative, right? It can be 0, but it can never go negative. Correct? Right? Yeah. If you put something through a resistor, you always get out positive power. And this is what we're talking about in terms of stochastic process. It's the power delivered on a 1 ohm basis. So therefore, the output of this filter will have an average power equal to the expected value of the output squared, which is equal to the autocorrelation at the origin. But at the autocorrelation at the origin, we said that was equal to the average power. It's also equal to the area under the power spectral density curve. So the area under the power spectral density curve is simply going to be the value of the input evaluated at the point f sub 0. So that means that this point at f sub 0 must be non-negative if this average power is to be non-negative. Which in turn means that all of the points on the input must be non-negative. So therefore, this shows that the power spectral density for the input is always greater than or equal to 0. Let me elaborate that and tell you the same thing with a little bit different verbs and maybe a little bit different pictures to possibly make it easier. We have an input x of t into a linear time invariant filter, and then we have an output y of t. There's something that we know in terms of any stochastic process, that any stochastic process that's wide-sense stationary, that the autocorrelation at the origin is exactly the same as the power spectral density integrated overall frequency is equal to the average power, which must be greater than or equal to 0. In fact, the only time the power is equal to 0 on a wide-sense stationary process is when the signal is identically 0, which isn't much of a signal, right? Isn't much of a stochastic process. So this is always true. And this should be a z here, shouldn't it? And this should be a z. Okay, so this is true no matter what. So here's what we're going to do. We're going to assume that we have a power spectral density of the input, which looks something like this. And what we'd like to show, what we're trying to show here, is that x sub x is greater than 0 for all values of x, or all values of f. That's what we're trying to attempt to show. The way we're going to do this is run this through a little bandpass filter here, and the output of the stochastic process is going to be equal to the input times h, where h is going to be a little bit a filter which is centered on the frequency f naught, correct? The output then is going to be equal to the input times the power spectral density, the power spectral density of the input times the frequency response of the system. Now I think you can see what happens here is that if we multiply these two things together, the height of this thing is 1. So if we multiply the two things together, we get that the output power spectral density of y looks like this, correct? That's the output power spectral density of y. Now, let us look then at the average power delivered by the output. What is the average power delivered by the output? Well, the average power delivered by the output, let's call it P sub y, is equal to the integral of the power spectral density of the output power spectral density function. In fact, that's the way we defined it, correct? So that being the case, this is equal to the integral. Well, the only thing we have here is f naught to f naught plus df. And within this interval, we're going to assume that df is so small that the value here at the origin, that the value at f naught is simply equal to s of f naught. So we're going to assume that this df is so small that essentially this little slope here is actually a constant. And we can do that. That's a very common calculus sort of assumption. So this is s sub f of times df, which is the same thing as s sub, this should be s sub y. This should be s sub x of f naught, which is the value here, times df, because that's the area of this curve. If we have a height of s naught and a width of df, then the total area is equal to s naught, sx f naught df, right? Our premise is that this average power is always what? Non-negative. This average power is always non-negative. Therefore, this expression must be non-negative. This must be greater than or equal to 0. Right? So if this is greater than 0, well, df is greater than 0 since we're going to the right in terms of our increment. df is greater than 0. It means that s sub x of f naught must be greater than 0. And not only must it be 0, it must be 0 for all values of f naught that we choose. We can choose any value of f naught up and down the frequency axis, and this is still going to be non-negative, correct? So what we have done is we have established that the power spectral density of x, no matter what that power spectral density is, must be non-negative. And we have used this filtering result in order to establish that. Any questions on that? Okay. Let's look at the case of filtering wide-sense stationary random processes in terms of derivatives. Whoops, went the wrong way. If x of t is differentiable, and we're assuming that it is differentiable, not all stochastic processes are differentiable. If you're interested in details, it is discussed in your text. And we're going to let y of t equal to the derivative of the output. Then the frequency response is j2 pi f. We've talked about this a little bit before. If that's the case, then the output of the random process is always equal to 0. And the power spectral density of the output is always equal to 2 pi f squared, which is the magnitude squared of this, times s sub x of f. So what is interesting in is that we do this. Shoot. Didn't mean to do that. Okay. So let's look at this. You agree with this? That the output is equal to the magnitude squared of the input. And the magnitude squared of J2 pi f is 2 pi f squared. Not minus 2 pi f squared, right? But it's 2 pi f squared. Is that okay? Okay. So we have this sort of case. Now, you'll notice that the output for a derivative is equal to this. And here's what we'd like to do. We would like to perform an inverse Fourier transform, and we would like to find out what the corresponding autocorrelation of the output is in relationship to the input. To do this, we have to be a little bit careful because this is the same as J2 pi f squared times a minus sign. Do you agree with this? That this follows? Now, why do I want to do this? Because I know if I multiply something by J2 pi f, what do I do to its inverse transform? I differentiate it, correct? And so, if I square it, that means I differentiate it 2 times and negate it. So therefore, if I inverse Fourier transform this using the derivative theorem of Fourier transforms, I get the following interesting relationship. I get that the output autocorrelation of a differentiator is equal to minus the second derivative of the input autocorrelation. So this is what happens to autocorrelations when you differentiate differentiable wide-sense stationary stochastic processes. Actually, this is really kind of neat because if you analyze this result, you come up with something which is nice in terms of a sanity check. We know that for real signals, the autocorrelation is even. It might look something like this. It has a maximum at the origin. Remember, the autocorrelation could take on only certain properties, correct? So let's suppose that our autocorrelation kind of looks like this. If we take the first derivative, you'll notice that the slope here begins to go negative. The slope at the origin is 0. So the first derivative is going to look something like this. That's what the first derivative is going to look like, right? Just graphically. Similarly, we have an interesting situation. We have a negative slope here. So if we take the derivative of this function, we're actually going to get something. It's a negative slope, so that means if we take the next derivative, we're going to get something which is, by the way, derivative of an even function is odd. Derivative of an odd function is even. Yeah. So this is what the second derivative is going to look like. Oh, you notice this second derivative cannot be an autocorrelation, can it? Because it has to be equal to a maximum at the origin. However, if we invert it, and we were to look at the minus derivative, we get something that, yeah, you know, maybe this could be an autocorrelation of sorts. If we took this function and flipped it around, if we negated it. And indeed, we get something which looks like an autocorrelation again, and what we have shown here is that for the derivative, this is indeed equal to the autocorrelation of y. So all of the properties that we require of an autocorrelation are maintained in this. They have to be. But it's kind of nice to go through it and do a sanity check and actually see that this is the case. Any questions? So this is the result that we have at the bottom, is that the autocorrelation is equal to minus the second derivative of the autocorrelation of the input. There's ARMA processes. ARMA processes are discrete processes where we have a discrete input into a system, and the input-output relationship is expressed as a, okay. I guess I don't have any more on this page. Let me show you what it is. The ARMA process is a white noise being fed to an IIR filter. How many have had 518 or 442 DSP? Okay, many of you had. You're familiar then with the concept of IIR filters. And the characterization of IIR filters. The input-output relationship of an IIR filter can be expressed exactly as on page 421 of your book. And you should be familiar with how you realize, you should be familiar with how these are realized using shift registers and some of the different forms that are used in DSP, although you're not going to be responsible for this in the course. The idea is that an IIR filter, this is a deterministic rendering, is such that if we put a sequence X sub n into an IIR filter, then the output is going to be Y sub n, and the relationship between the input and the output is given by this expression. What happens is that the output takes advantage of previous outputs. This X of n minus I corresponds to previous outputs that have already occurred. So this is actually a feedback mechanism weighted by some tap values of alpha sub I. So they're fed back in a linear fashion, and you take a linear combination of a set of Q previous values, you add it to a weighted combination of the most recent inputs, and that corresponds to your output. These are extensively studied because they're very, very easy to build in terms of their architecture, and they have some very, very useful properties. An ARMA filter is exactly the same as this, except that the filter is exactly the same, but instead of placing into the filter an arbitrary value of X sub n, we are going to place white noise into the filter. We're going to place white noise into the filter, and then we are going to observe the output, which we will call Y sub n. Clearly, if this is a white noise process being put into the filter, the output is also going to be a stochastic process. Now, just like differential equations or anything else dealing with this, we obtain the input-output relationship borrowing from the deterministic equivalent, so that the output in this case is equal to the following. This is exactly the same equation that they used to describe the ARMA process on page 421 of your text. So this expresses the current output in terms of previous inputs, or previous outputs, plus weighted values of the P, most current values of the input. And you notice the reason that we have it written this way is we have the current output, the current value in terms of past values, or the current value of the input, but except for the current value of the input, all of these are past values that have happened in the past. And we write it that way because it kind of shows the flow of the operation very nice. And once you get the current value of Y sub n, you can stick it back here and compute Y sub n plus 1, stick it back here, etc., and do this in a recursive sort of manner. However, computationally, if we're not interested in causality, this has a nicer representation if we take this to the other side and we simply write the expressions thusly. I is equal to 0 to q of alpha I, y sub n minus I. That's equal to the summation of I is equal to 0 to p of b sub I w of n minus I. This then is the result, and the alpha sub 0 is equal to 1 in this case, because what I've done is I've taken this to this side, gotten rid of the negative value. I've sucked the y sub n in here corresponding to the I is equal to 0 case, and since this doesn't have a coefficient, we're going to call alpha sub, I'm sorry, that should be alpha sub n. No, alpha sub 0. Alpha sub 0 equal to 1. Okay, so those are equivalent statements. The reason we do it this way is because it's very nice to be able to compute the frequency response of the system. And the frequency response of the system we can get by looking at the equivalent deterministic case. And now we want to represent this in the frequency domain. We can represent it in the frequency domain by taking the discrete time Fourier transform of both sides. And if you recall, if we have a relationship that says z sub n has a Fourier transform of z sub f, that's the definition of the discrete time Fourier transform. Then what happens to z sub n minus I? What does that Fourier transform to in discrete time? It's z of f times e to the minus j 2 pi I f, right? Just like in the continuous domain, continuous time domain, a shift in this n domain corresponds to a multiplicative phase term in the frequency domain. This being the case now, then we can perform a Fourier transform on both of the sides here, and we get the following relationship. And then, of course, what are we after here? We're after the frequency response of this ARMA system, or this IIR filter, I should say, which is a linear time invariant system. And that, of course, is just equal to the Fourier transform of the output divided by the Fourier transform of the input in discrete time, which is equal to the ratio of these two results. So let's see, y, dum-dum. So this is the frequency response of an IIR filter in terms of the tap values. Of course, don't forget that alpha sub 0 is equal to 1 here in our characterization. These, by the way, are sometimes referred to as trigonometric polynomials because they are kind of like polynomials, except that we have trig functions here. And there's a finite number of terms, hence making it a trigonometric polynomial. So the frequency response of an IIR filter is always equal to the ratio of two trigonometric polynomials. So this being the case for the discrete time system, we immediately have our handle on what happens for the stochastic case when we feed this IIR filter white noise. For a ARMA process then, autoregressive moving average, by the way, is what the acronym stands for. The output power spectral density of this discrete time system is equal to the magnitude squared of the frequency response times the power spectral density of the input. These, of course, are discrete time power spectral densities. So in the case of an ARMA process, what is the input equal to? It's equal to N0 over 2. It's white noise. So therefore, it is a input which is constant for all values of time, is the assumption. Now, this can be realized. There's not, for discrete white noise, as we talked about last time, there's nothing infinite about it, nothing magic about it. It's something which can be realized. It's continuous white noise that puts up the little flags, but nonetheless is very useful and a very powerful model. So in this case, the output power spectral density is equal to N0 over 2 times the magnitude squared of the ratio of these two trigonometric polynomials. In many cases on these processes, and this will not be a topic of this course, we would like to actually have some sort of representation of the power spectral density of the output, yet we don't know what the values of beta and alpha are. So there's a synthesis procedure that one goes through if one knows what the output power spectral density is going to be by essentially training and adapting these alpha sub i's and beta sub i's to fit your design criteria. But that's the synthesis problem. We're looking at simply the analysis problem, where if you are given a IIR filter with white noise input, referred to as an ARMA process, this is the power spectral density of the output. The alpha and betas are the parameters of the IIR filter, and the N0 is the power of the white noise. Any questions on this? Autoregressive moving average. You'll notice some interesting results here. One is that if all of the alpha i's are equal to 0, then we have something which is called a moving average. And what this moving average does is this moving average takes the input process, which is white noise, and then whatever the value is of p, it does a weighted average of all of these p's. It multiplies this one by a beta, 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 weights all of these and adds them up, and that corresponds to the output at that point. So in other words, there is no feedback in the moving average sort of thing. So if you have a process wherein you're actually performing a weighted average, it's weighted average because each one of these is not weighted by 1 over n, each one is weighted by a corresponding value of beta, then one has a moving average process, which is something that one uses, for example, for smoothing operations, correct? In image processing and signal processing and such. So therefore, if you have a stochastic process and you do a moving average on it, then your relationship between your input and your output power spectral densities is given by this equation with all of the alpha i's going to 0. Okay, any questions on that at all? So let's summarize the autocorrelation final results summary. For both discrete time and continuous time, we get this relationship, which we've seen 2 or 3 times before. And the exciting thing about it is wide-sense stationary processes are totally traceable through linear time invariant systems. You can track them. You can keep track of the average. You can keep track of the autocorrelation, power spectral density, same thing, by these 2 sets of equations. Okay. Okay, we done there, done that. Tell you what, let's do our break right now, and let's take it a little bit early today and meet back here when the big hand's on the 4. Is that okay? Good. Good evening. We got it right. Okay, we're going to have our last lecture on stochastic differential equations, which are very much like the IIR filters, as we'll see. Before we do this, by the way, in the last section, you flip back a few. It's material that we skipped the first time through, because I wasn't sure that we would have time for it. You see it? Okay. Excuse me, I amused myself right there. Okay, it's okay. Let's recall that if we have y of t as a derivative of the input, we're going to do something now which we didn't do before. We're going to generalize. We're back at non-stationary processes. In other words, these are processes where a function of t and tau. So this is a more general case than we talked about with the ARMA process, where we restricted our inputs to be wide-sense stationary. So if we do have a process which is not stationary, then all of that stuff about power spectral densities, all the stuff about the characterization of a stochastic process and the frequency domain goes out the window. We don't have conventional tools to do it. There are other tools to do it, but they're not very widely used because they're more cumbersome. So let's assume, again, a non-stationary process, and this is something that we went over last time. If the output is equal to the derivative of the input for a non-stationary process, then the autocorrelation of the output is equal to the partial of t and tau of the input stochastic process. So this is a simple tracing of a autocorrelation of a non-stationary process through a differentiation operator. We're going to generalize this more to the idea of non-stationary stochastic processes and differential equations of these processes, referred to as stochastic differential equations. Now, where do these equations arise? Everywhere. Remember Kirchhoff's laws? Suppose that you had a Kirchhoff's laws and you wrote down the Kirchhoff's laws and you were trying to get the output, the voltage of some capacitor in accordance to the voltage of some voltage source of some input somewhere on this complex linear circuit. You would come up with a differential equation of this sort, application of Kirchhoff's laws. In fact, sometimes they might even be coupled. We're not going to do the coupled version, but we're going to do just a single version like this. If you have in mechanical systems a mass, a resistance, and what's the other thing, a spring, and you are to look at an applied force to a system composed, mechanical system composed of these properties, you'll come up with a differential equation that looks like this. So it's a very powerful set of differential equations. I don't know if they still teach you can solve many mechanical systems using circuits. Is that still taught at all? It is, okay. So the reason is that the differential equations go through many different systems, but their actual form remains the same. So imagine one of these systems, and suppose that x of t, which is the input now, is a stochastic process, and it's some sort of non-stationary noise. And we're characterizing it by its mean, for example, and its autocorrelation. So the voltage source in your circuit, in your linear circuit, is noise. This assumes total linearity. It assumes time invariance too. Oh man, I forgot something. Whew. Oh, this is terrible. Ladies and gentlemen, this is terrible. Let's see if I... Oh, there it is. Okay. Whew. There should be A's here and B's here. I'll show you the next slide. That's what it should be. Whew. Man, if I forgot those throughout the whole thing, that would be inexcusable. So we have the B's and A's here. They're much like the alphas and the betas in the IIR process. In fact, this is the continuous representation of the IIR sort of process. So I'm going to go back and I'm going to put up this equation without the coefficients. Ignore that. And let's look at our problem. Given the non-stationary correlation of x, find the forced solution for the output. We will find out that with stochastic differential equations that indeed we can do that. We said we could do it for any linear system, and we showed you ways to do that. Now, if you recall, the way that we did this for non-stationary inputs is usually generated a catalyst, which was the cross correlation, and then we generated the cross correlation and used the cross correlation to compute the autocorrelation of the output. Do you recall that for the general methodology of the linear system operating on a stochastic input? We do the same exact thing with the stochastic differential equation, so let's take a look at that. First thing we're going to do is determine the cross correlation. And the way we're going to determine the cross correlation is we're going to take this equation here. These are constant coefficients of the differential equation. Because those don't change with respect to time, this is a time invariant system, right? And in order to do the cross correlation now, we're going to multiply both sides here by x of tau. So I'm multiplying this side by x of tau and this side by x of tau. Then we're going to do expectations. If you recall, derivatives commute with expectation, which is a very nice thing to have on our side at this point, because if we perform an expectation on both sides, we get the expectation of this and we get the expectation of this. What's the expectation of this? It is the cross correlation. What is the expectation over here? It is the autocorrelation of the input. So if we recall this commutativity? Commutivity? Is it commutativity or commutativity? Commutativity, okay. We get the relationship on the bottom of the screen here. Now you notice there's nothing stochastic about this. This final equation is deterministic. This final equation relates the cross correlation of t and tau to the autocorrelation of the input. And these are known functions. We're going to assume that we know them. And again, they're not stochastic anymore. So we have reduced the stochastic differential equation to the case of finding a deterministic solution of a differential equation. It might be confusing at first to look at this and say we have two-dimensional variables here, but you'll notice that all the derivatives are with respect to t. Therefore, tau is just a variable that goes along for the ride. Tau is a variable that goes along for the ride. We fix tau and we solve this as a function of t. So it is a typical first-order differential equation, single-dimensional. Tau can be thought of as just a subscript, and we solve this as a function of t, which is something that we can do. Now, when we solve problems of this type, and when we have a non-stationary process, we can imagine that the concept of transients will appear in the equation. Transients are typically dictated by the initial conditions of the process. And if we have a differential equation, and we're not solving it in steady state, by the way, when we're solving something in steady state, what transforms do we use? Use Fourier transforms, because Fourier transforms are from minus infinity to infinity, so all of the transients have died out. If you're talking about transients, what do you use? Unilateral Laplace transforms, because the unilateral Laplace transform starts at 0 and takes into account the transients. Okay? We're in the latter sort of stage here, so we have to be careful about this. So fix tau and solve the differential equation. Forgot my A's and B's here, ladies and gentlemen. The particular solution, assuming 0 initial conditions. Here's what we're going to assume in terms of the initial conditions. Now, if you remember, differential equations have a forced or a particular solution and a homogeneous solution. The forced solution is that due to the input. That's what we're interested in. We're interested in the forced or the particular solution of the differential equation, not the homogeneous solution. So therefore, to get rid of the homogeneous solution, we set all initial conditions equal to 0. That's what we're doing. You'll notice that if we set all the initial conditions to 0 for the input, then we have, if we multiply by x of tau, we get that the derivatives, multiply by x of tau and then expectate. Is that a word? We perform an expected value. But doesn't expectate sound better? It doesn't. It's more. No, it doesn't, does it? Sound like spitting. Okay, we perform the expected value. So we perform the expected value, and what we obtain is that the initial conditions for the differential equations corresponds to the autocorrelation at the origin for a fixed tau. Don't forget, tau is just going on for the ride, is equal to 0. So this is something that then we can solve. We have a differential equation with initial conditions. We can solve the differential equation. Again, the a's and the b's should be here. Now, doing this, though, just gives us the cross correlation. We are interested in the autocorrelation of the output. The cross correlation is kind of a catalyst which allows us to get there. So how do we find the autocorrelation for y? We start with the original equations with the missing coefficients. There should be the a sub n's and the b sub n's here, b sub n's here, a sub n's and b sub n's. And now what we're going to do is we're going to there they magically appeared. We're going to multiply both sides by x of tau. Remember, before we multiplied both sides by y of tau to get the cross correlation. Now we're multiplying both sides by x of tau because when we expectate, we find that what the heck? Boy, this is all messed up. Forget this stuff. Here's what we get. We get the summation of this times the derivative of the cross correlation is equal to another thing by the autocorrelation, right? Now, we're assuming we know the input. We assume we know the autocorrelation of the input. Do we know the... That's terrible. That's totally incorrect. Totally incorrect. Okay, well, okay, that's why God gave us whiteboards, huh? I'm going to have to do this on the board. Here was the first thing that we wrote, and this was tractable. A sub n. Okay, so this is the result that we have for the first differential equation. Now, this I maintain that we can solve for the cross correlation if we're given the input autocorrelation, right? Okay. Now what we're going to do is we will write down the same differential equation again. What's on this side? X of t? Okay, now we're going to multiply both sides by, is that right? Yeah, that's right. Is that right? Yeah, I just might cancel this whole lecture. A sub m, I'm getting my A's and B's wrong. There should be a BN. There should be an AM. There should be an X. Right? Okay. Now what I'm going to do, are you sure it's right? If I make one more mistake, we quit and go home. Okay. all of a sudden everybody's paying attention. That'll be the way to do it. Okay, what we do now is we multiply both sides by y of tau. And then what do? Expectate. That's right, we take the expected value of both sides. By the way, expectate is not a word. Okay. I don't want you to go out. You know, one I hear quite a bit is convolute. You take two functions and convolute each other. So that's not a word either. It's a word, but you convolve two functions. You don't convolute them. Okay, so anyway, we have this expression. And we have this expression, which is a very interesting expression. This expression also has some initial conditions, and that initial condition would be, as before, that the derivative of the forcing function of, it should be the output, is equal to 0. So therefore, this corresponds to that all of the derivatives of the cross correlation, the derivatives of y, of the output are equal to 0 also at the origin. Therefore, the crux of the matter is, details not being important, is that if we have this differential equation, we can do a couple of things. We can solve this differential equation using these sets of initial conditions. This is our original differential equation. This is what we're trying to solve without the red. Yeah?
On the blue text down there, is it y is 0?
Oh, yes, it should be r sub y is t and 0. Is that?
Oh, no, on the left side, isn't it y is 0?
Yes, it should be y is 0. Thank you. Yes. Good. Hit the point. Okay, so we use these differential equations. We solve for the autocorrelation. Got it? No, we don't. We solve for the you're not going home. You solve for the cross correlation here. Once we solve for the cross correlation, we can come down here and we can solve this, where the cross correlation now becomes our input, and we solve for the output correlation using these initial conditions. So just like in the other cases that we looked at, we first of all do the cross correlation as the catalyst to get us to the final example. And then once we get the cross correlation, we can use the cross correlation to compute the autocorrelation of the output. Okay? So that's the kind of a quick overview of the solution of stochastic differential equations with a non-stationary input. This is a pretty powerful way of doing things. I'll clean the slides up and get them on the web. Sorry about that. Okay, that concludes all of the lectures for EE505. No, thank you. On the examination, you will not see ARMA processes, and you will not see stochastic differential equations, okay, on the final examination. So I tell you that now because if I would have told you that before, what would you have done? Okay, so those will not be on the final examination. With that, we do have a few minutes, and if you would like to, I can answer any questions that you have about the final examination. And if there are none, what I'll do, in fact, let me do this now. I'm going to hand out these sheets. These are the course evaluations, okay? And everybody in here is getting a 4.0. So you make sure you give me a 4.0 also, okay? Oh, it is being recorded. No, just kidding. Just kidding. We don't want to leave any smoking guns here. Okay, I'm just kidding about the 4.0s. I thought you could tell I was kidding by the tone of my voice as I was doing that.
I think we all got some lattes.
That's right, kind of as a payoff. Would you collect everything and drop it in the mailbox? What you do is, when they hand it in, you stick it in this envelope and you drop it in the campus mail somewhere.
Okay.
Okay? And I'd appreciate that. So when you're done with that, I'll be leaving before you hand it in, so I'm not going to be looking at what you're doing. Any questions then at all? Okay, if not, then Thursday, 10:30, office hours, if you have any specific questions. If you come and there's somebody else in the room with me, come on in. You might be answering the same questions that you had. And, yeah. How many questions? There will be 5 or 6 questions. If you need tables, I'll give you tables. Okay? Okay, thank you. That's it. Signing off. This is Bob Marks saying goodbye.
La